Engineering 305. This is problem 8, chapter 8, problem 16. This is a longer problem, special request problem, and it's typical of the problems we get in chapter 8. They're very long. They've got a lot of steps. You should have a plan from the beginning, but the plan is fairly simple. Also, we calculate all of the integrals with all the constants to get us these equations that describe the deflection of the beam, and then we solve for a series of constants which came from our integration steps using boundary conditions. And so normally that's going to involve 2, 4, 6 different boundary conditions that need to be applied in order to get the information we want. And this problem is no different. So let's walk through this. A boy with a mass of 60 kilograms is standing on the end of a diving board, and it's got geometry properties and material properties. So what I'm going to do, I'm working on this right below it. It's got E and I. Shouldn't be surprised, right? That's fundamental to what we're doing. So if the length of the board is 0.6 meters, that's from A to B, so that's this distance here, is 0.6, I'll say 0.6 meters, and this distance is 1.5 meters, there to there. Determine the maximum deflection in the diving board when the boy is standing at the end of the board. Now, they gave us his mass. He's about 120 pounds, but really what we need to convert that to 588 newtons. That's equal to 60 times 9.8 meters per second squared, and that's going to give me the quantity newtons that I'm looking for. Now I can do a free body diagram, a proper free body diagram. I'm going to have reaction force here, and I've got the weight of the diver here. And I think if you look at this, you realize that's not right. It's this. My reaction at A pulls that down. My reaction at B pulls that up. And here's my 588 newtons. And so then if I go through this, some of the forces in the Y are equal to 0 are equal to minus RA plus RB minus 588 newtons equal to 0. RA, well, I'm leaving it alone. Leaving it alone. That's not enough. I need another equation. I need some of the moments. Where do I want to take the moments? Around A or around B? Which one do I want to eliminate? It doesn't matter. I'm going to go around B. A is going to cause a positive moment. So that's RA times 0.6. And then the 588 is going to cause a negative moment. So that's a minus 588 times 1.5. And from all of that equals 0 equals RA is equal to, and we got to either go to calculator time or I got to pull up my answer over here. RA is equal to 1,470 newtons. When I plug that back into this, RB is equal to 2,058 newtons. All right? So that's where I am. I've got my boundary conditions. So now if I would want to, I could draw a shear diagram as a function of x, and I would be at minus 1470, and then I would pop up to 1470 minus, it'd be 588, because all the way at the end here I drop down. So this is 588. So there you go. There's our shear diagram. Now our moment diagram. Well, we start at 0. And we start going down a slope 1,400 I know what my slope is. It's just, yeah, we're not going to do that. We're going to write the equations out. We're going to write the equations out. You realize this is just the integral of that. But my shear, sorry, in black, I'm going by the black. My shear is equal to minus 1470 for x's between 0 and 0.6 meters. And it's equal to 588 for x's between 0.6 and 2.1 meters. 2.1 because it's 0.6 plus the 1.5. Right, not a surprise there. I'm going to integrate that. My moment equation is equal to minus 1470x plus C1, and this is equal to 588x plus C2. 0x up to 0.6, and this equation is good from 0.6x up to 2.1. Keep going. Theta, well, it's not theta. It's not theta, it's EI theta is equal to, maybe I should put equals there, is equal to minus 1470 x squared over 2 plus C1x plus C3. That first equation is going to have odd constants to it. The other equation will have the even constants to it. 588 x squared over 2 plus C2x plus C4. And I'm not going to write the limits in there again, but you know where those equations are good. Lastly, EI delta is equal to minus 1470 x cubed over 6, 588 x cubed over 6 plus C1x squared over 2 plus C3x plus C5. This equation becomes C2x squared over 2 plus C4x plus C6. 6 constants to evaluate. I need 6 boundary conditions. Ugh. Who set us up for this? Who picked this problem? Oh, wait, that would be me. It's kind of a fun problem because it's a real problem. It's a kid on a diving board. It's a fun problem. So, boundary conditions. I know, well, I don't have any shear. I mean, I know the shear at the ends is, well, I don't really know the shear is 0 at the ends because it's already jumps to a constant. That's why I drew that. But I do know that my moment at the end is 0. So my moment at 0 is equal to 0. So that's going to get me this equation, that one, is equals minus 1470x plus C1. X is 0, so C1 is equal to 0. And now, and this is boundary condition 1. So now I could start going through and I could say 0 BC1, 0, 0. So I don't have to deal with that anymore. Do I know anything else? Well, okay. I know that my displacements at 0 are equal to 0. Are equal to, and that equation, Kung Fu, that equation is this one, right there, Right there, I'm going to have a lot of lines if I keep doing that, so I'm going to get rid of it. That's equal to minus 1470x cubed over 6. The C1 term went away, plus C3x plus C5. So the first two terms go away, and C5 is equal to 0. That's based on boundary condition 2, and so that's this one. All right, so far I've picked off the boundary conditions that are, I've been saying the boundary conditions at x equal to 0 are easy. It would be nice if we could solve C3 that way. So do I know anything about the slope at the beginning? Here's the problem is I know that this diving board is going to go up and it's going to come down, and I know the deflection at both ends, and then this is going to come down and it's going to continue to bend. I don't know the slope anywhere on this thing. But I do know, unfortunately, that the deflection at L, not at L, I don't even have L in this problem. I do know the deflection at point 6 on the other end under that first stub is equal to 0, and that is not an equation that's equal to 0. That's that one there, and that's minus 1470 x cubed over 6 plus C3 times x. Yucky, yucky, stinky poo. Yeah, it is. It is. But we can solve that. So let's jump to our trusty dusty calculator, and you know what we're going to get? We're going to come away with, it's going to be C3 is equal to, equal to 88.2. And then I put units on it, Newton meters squared. And the reason you're going to see that this was, this is the 1470 is in newtons, and then that's going to be the length, the distance is going to be in meters, and these need to be consistent. So Newton meters squared times meters is going to give me the consistent units all the way across. Excuse me. So now I've got equations I've got constants 1, 3, and 5 identified, and I'm ready to go forward. Do I know? Am I ready to go forward? Sure. Let's keep going. I have to determine all of the constants 2, 4, and 6. So do I know anything about, the easiest place to start solving constants, do I know anything about the moments any place? For the second equation, in this range, do I know anything about the moments? Well, yes, actually I do. I know that the moments at the end where the boy is standing are 0. They go to 0 at the end. So the moments at 2.1 are equal to 0 are equal to 588x plus C2. 588x plus C2 are equal to, and so that's 588 times 2.1 plus C2, and so C2 is equal to, back to the calculator, but that's going to give me back to the calculator. Hold on. So that's a negative 1234, and the units on that are going to be Newton meters. And that makes sense. It's a constant that shows up in the moment equation. It should have units of Newton meters. Okay, so now I can start going. Do I know what else? What else do I know? Do I know the angle anywhere? No, I don't know the moment anywhere else. I guess I know I do know the deflection at 0.6 is equal to 0, and that's true with this equation too. So I can use this equation from the other side. I already used this equation from the left, and now this equation from the right. And so that's going to be equals 588 x cubed over 6 plus, I have C2, right? I just solved for that. So that's minus 1, 2, 3, 4. Oh, you know what? I got to get rid of that. And I got to go to blue. Minus 1, 2, 3, 4. That's C2. And then that's x squared over 2. And then plus C4 x. Sorry, I didn't want to put that in there. Just rewrite that. C4x plus C6. All right. You already realize that's not going to help me, right? Because I got to put in a number, and I'm going to get C4 and C6 in the same equation, so that didn't help. Do I have another boundary condition? Well, I do. In the same way we're using this equation, we're using this from the left and from the right. I can do the same thing here, that this from the left and this one from the right, they have to equal each other. So I'm going to write that theta from the left at 0.6, that's equal to this minus 1470 x squared over 2. C1 went away, plus C3. I solved for C3. It's 88.3. Plus 88.2. Is that right? Okay, so minus and then a plus. Minus that, plus that, and it's C3's down there. Okay, and that's going to be equal to this minus a 588x is equal to theta from the right at 0.6 is equal to a 588 x squared over 2 plus C24 plus C4 plus C2 is right there, so that's a minus, so I'm going to C2x, yep, 588 minus 1, 2, 3, 4 x plus C4. And I don't know what the number is, but I know those have to equal each other, right? Okay. So 1470. So I'm going to jump to the calculator, and I'm going to punch this term in and write it below, and then that term below. So I know that plus 88.2 equals, and then this is going to be, I'll punch that one in and get that, and then I'll punch that, and then I'll have C. Be right back. So now I've solved for C4. So really I took the 264, 88, and I got a negative 175. And then I added those two together, I got negative 634. And then I added 634 to both sides, I got positive 640. Boom, I solved for C4. Now I'm ready to crunch in there, because now I know everything there. I can write down 0, the deflection at 0.6. 0 is equal to 588 times well, I just put it as 0.6 cubed. 0.6 cubed over 6 minus 1, 2, 3, 4, 0.6 squared over 2 plus C4, which is 460 times 0.6 plus C6. And now we just crunch all those numbers. And so, yeah, you're right. Goodbye. So I solved for that. I punched in those. I got 21.7. I punched in this. I get 221, 222. I get 276. Boom, I got that. C6 is negative 75.1. So now we're looking at the deflection. We want to know the deflection at 2.1. Wow, that's equal to, I have this equation right here. Oh, it's way back, isn't it? It's not even there yet. It's way back here. And now I can punch in all the constants and get to where I needed to be. So 588 x cubed over 6. 588 x cubed over 6. And then I'm going to say it's plus, but it's plus C2. So C2 is there, minus 1, 2, 3, 4. And that's x squared over 2. Minus 1, 2, 3, 4. X squared over 2. And then I got my C4 term, right? C4x. C4 I solved way down here. 460 is positive. So that's going to be plus 460x. And then a minus 75.1. There is my equation. Now punch it in and solve it. And if I punch it in, I'm going to get, well, this actually, sorry, I got to write an EI out there. Now, E was given to us. I, really, do you need to know I is equal to the base times the height cubed over 12? You guys can solve that. This is going to give me the deflection at the end of the diving board is equal to 57.9 millimeters. It's going to be a negative 59. Sorry, it's not even going to be that at all. I'm writing down the answer. I would actually have calculated this to be 0.0579 meters negative or 58 millimeters down. Shouldn't be a surprise, somebody jumping on the end of, or standing on the end of the diving board, that they're going to cause the diving board to go down. All right, that is a long problem. That, even without TV timeouts for calculators, long problem. Questions? Of course, there are no questions because it's a YouTube video, so there's no questions. There's none at all. I hope you're doing well. See ya.